Okay, when we did our experiment on stretching springs, we found that that force applied to the spring makes it extend, delta x, and we get a straight line relationship, and the gradient of this is called the spring constant, K. And also we saw that when you stretch a spring you store up energy, and that the energy is the area underneath the graph. So we have the work done on the spring equals half force times the extension, and this equals half k delta x squared. Okay, if we go to a metal wire now, we talked about, instead of plotting force against extension, we plot something called stress against strain. And the reason for all this is that wires will be affected, the stretch of a wire will be affected by the length of the wire you have and the cross-sectional area. So what we do is we normalise, so instead of plotting force, we plot force over the cross-sectional area, which is of course stress, and the strain, which is the change in length over the original length. But in this case, what does the area under the graph represent? So we saw that the area under the graph for the force against the extension is basically the work you do on the spring, so it's the energy stored in the spring. But in the case of stress and strain, what do we have? Okay, well, let's work out the area of this shaded area. So if we do, it's going to be half base times the height, half F over A times delta L over L, and we end up with F delta L over A times L, and there's a half there. So on the top we have half force times the extension, delta L, and on the bottom, that was L, we have cross-sectional area times the original length. Okay, well, if we look at this top thing, which is half force times the change in length, it just looks like what we had for the spring, half force times the change in length, the extension, and we could see that that was the energy stored in the spring. The work done on the spring is the energy stored in the spring. So you can see here that we have on top, we have the work done on the spring, on the wire, divided by the area times the length, where an area times the length is a volume. So what we have for a wire is that the area underneath the graph is actually the energy stored per unit volume.